All right, time for another DraftPhysics.com, debatephysics.com, also video presentation. So, continuing the conversation with the very few commenters with no evidence. Okay, they just keep making abstraction arguments, either mathematical abstraction or thought experiment abstractions, and it's all such a desperate effort to, in some way, I don't even know what the the obligation is to demonstrate something to be true. Okay, that this mv 1/2 mv squared gets actually does work somewhere. So you have to just show where it actually produces what you claim it has when you change what it has to do it to. So every time the simple argument is because of the squared velocity, is that you're doomed. You're either going to create free energy or you're going to lose energy, because every time you change the mass, you end up having to change the velocity in some perverse way that's going to distort and pervert what kind of momentum you have, and you can't conserve the momentum. So anyway, I think I've proven the point over and over, and they just keep doing this crap. So some asshole called Mophead, okay, so he's written a little story, and of course the story doesn't come with diagrams or anything else, so I'll have to provide all of that. Annoying. Yeah, what the hell happened here? All right. Here's an easy way to understand why you can create heat without losing momentum. So there's no idea that this is a possibility. You can't make motion in the universe and keep the motion you have. You can't do it. You can't share your motion and keep your motion. You can't give your motion and still have your motion. Can't happen. There's no example anywhere that this is possible, and yet he's going to try to defend this idiotic bullshit. All right, you have a ball and a box. Both have the same mass. You make the ball move 10 miles an hour. It hits the box on one side and gives it momentum to the box. Now, this is an example I've already used in the sense of understanding how motion does work in the universe. All right, well, anyway, now the box moves until the opposite side hits the ball. So the ball has to be in space because the ball is going to stop moving. And obviously we can't have rolling because that's going to be friction and you're going to lose energy. So let's say you're in space, you have this box, you throw a ball into it, it hits one of the surfaces, then the ball stops. So it's a perfectly kinetic, in the sense that it's a perfectly elastic collision. And so you're going to put all of the energy into the box, because the box has the same mass as the ball. And so then the box is going to move, the ball is going to stay where it is until the back end of the box hits the ball. Then the box is going to stop and the ball is going to move again until it hits the front of the box, and the box will move. So the box is just going to jerk its way in one direction, the direction you started to give it motion in. All right, then the ball hits the box again, and so on. The object alternately have 10 miles per hour velocity. Note how the total momentum is conserved, and the average velocity of the objects is 5 miles an hour. So if you combine the two objects, you end up with 5, but it's really 10 miles when they're moving. Okay, so one moves, the other one stops. One moves, the other one stops. So that's why it ends up being 5. So while they're moving, they're still only going 10. That's the maximum velocity. Okay. Next, let's make the box smaller and smaller until the ball can just barely move inside of it. Okay, so now it's not really vibrating, in the sense that it's going back and forth, but the box is still moving in one direction. So the box isn't vibrating, it's jerking forward. And it's still only going 5 miles an hour. 10 when it's moving. Do you see what happens? The ball turns into a vibrating object traveling 5 miles per hour. Vibrating in what way? It's just going forward at 5 miles an hour. Okay, the total momentum is conserved. Well, you haven't lost energy to anything because you're still moving the box. Okay, but now we also have this vibration energy. So right there, you lose. So as soon as you're vibrating something, all right, then you're going to argue that you're going to radiate it to the universe. So it depends on how fast the vibration is. And the fastest your vibration can be is 10 miles an hour. That's the fastest the box ever moves, is just 10 miles an hour. So when it's, say if I make the box move so little, an infinitesimal amount, then you can understand that all I'm moving is the electrons, and I'm still only moving them 10 miles per hour. So I'm not moving them. I'm moving them, 1/millionth of this, less than 1/millionth of the speed of light. If we allow a one-dimensional vibration to turn into more chaotic movements of particles, so I don't even know what that means. You defined your thought experiment. It's a closed system. You can't all of a sudden just make up some chaos. We will have a measurable increase in temperature while conserving the total momentum. So there's no measurable increase in temperature, because if the temperature is increasing, it means the electrons are all vibrating, right? But they're only vibrating at 10 miles per hour. They can't vibrate any faster than that. So you're just saying, I'm not going to move all of them, because moving all of them is moving the box. If the box isn't moving and the box is just vibrating, then you're not moving all of them. Okay. But losing half the kinetic energy it had in the beginning. So none of that will happen. So if you make it vibrate at with enough electrons moving enough speed, then they'll radiate their energy, because it will be absorbed by the environment. So that's the key argument, is how do you lose energy? So in a sense, this isn't nonsense, but it's nonsense in the sense that he's describing something he can't physically create. So that part's nonsense. It's a thought experiment. Yes, it's an interesting one, but it has a flaw in the sense that what I've been arguing all along, which is you're not understanding how motion works. So the idea is if you have a substance, all right, and it's made of pieces, okay, and the argument is you're going to apply a force to it. Okay, you're going to hit it. Okay, now you can do different things can happen. You can hit it, and then some of the electrons compress on the surface, but the compression doesn't move through the whole surface. And so then it just pushes back again. And so the energy just does a U-turn. And this side of the box never even knows anything happened, because there's not enough energy to move all of the electrons. So the only way the whole box can move is it has to move all the electrons. That means every single little piece has to have an element of force pushing it. So you have to have the force move to all the pieces and give them all a proportional amount of velocity so they can move the whole object. And if the whole object doesn't move, then you have the elastic quality, where it basically just U-turns the energy. Okay, it just says, yes, you put pressure in, but the extra pressure you put in is now extra pressure, and it's going to just push it back out again somewhere else. So you don't keep it. And so you can't have this circumstance where so the idea is you either move the box or you don't move the box. If you don't move the box, you're getting a reflection. If you move the box, then you've used the energy, okay, moving the box. And the idea is if I move the box at 10 miles an hour, I'm not going to lose any energy to space. So we know we can move things very slowly through space, and they don't get retarded in some way. So if there is some idea of drag, it's not very effective at very slow velocities. So it's a hard math to do. I mean, you have to figure out how much per second of distance you lose to the differential between, the force coming in at the speed of light and the differential created, from your pushing force. So if you're going into the force, but the force is going the speed of light, you can understand that there's still a lot of force still going to push you from behind because you're not going very fast. So you're not missing too much force pushing you. All right, and you're plowing into more force coming against you, but the differential in the speed is so high that how much realistically is the drag, per unit of time. So anyway, that's be an interesting calculation. So I think the fastest thing we've ever put into space is going 1/1700th, okay, of the speed of light. So it's not going exactly very fast, even though it seems fast from our perspective, in the sense it's the fastest thing we produced. It's still, a small percentage of the speed of light, and so it's you have to figure out. I haven't done that math, but it would be interesting to see how much distance per unit of time you'd actually lose to drag. Okay, but the part of the argument is where we know that things don't lose much energy to drag when we throw them in space. So even from the slower satellites, we know they don't get dragged to a halt. So we know the amount of drag is minimal at slow speeds, or there's some mechanism in that complex matter, the helium nucleus and up, that allows it to defeat the drag. So I've sort of pointed out that I believe the solution to that problem is when you're running into more force, okay, from drag, what you are doing is minimizing the amount of force that's hitting you this way. So it's just like the friction argument. As you go faster this way, less energy per inch is hitting you this way, okay, because it's all time dependent. There's a certain amount of energy is going to hit you in a certain amount of time, and as you go through that field quicker, less time for the energy to hit you. So there's less pressure pushing this way when you're pushing into more force this way. And the idea is that atoms have a more complex arrangement. And so you could argue that when you're putting extra pressure this way, going into a field of energy, that you're applying less pressure this way and this way. And that expansion in some way creates an elastic effect that creates more forward pressure to compensate for the drag. And that's why you're not dragged to a halt. All right, so I didn't really intend to talk about drag, but it's an important part of any of these conversations. The thing I really wanted to get to was the nature of photons and the difference, one of the major differences between how I understand photons to function and how you people understand them. So you think that the energy of a photon, or the photon itself, is something actually created by an object. So if I have a glowing filament, let's say, so I've put energy in, we know that there's impurities in the filament that's likely, okay, going to create some opportunity for heat, and that the hotter the filament gets, the higher the resistance gets, and the hotter the filament gets. So the two things are kind of, well, it's stopping it from cycling out of control. Let's just say that, because you get less electricity through the wire, and less electricity means less heat. All right, but anyway, so the idea is that we have this idea that we're putting a force in, and the point would be is that you have to collect the force again at the other side, that the amperage is, say the voltage is the pressure, so we could argue it's the same as speed, so we could say it's the same as velocity, and the amperage just has to do with how many bits of electron you're pushing. All right, so that's one way to understand that it's very similar to momentum. The amps are the mass and the volts are the pressure, the speed. How fast you're jerking an electron, or how far you're jerking the electron, probably another way of saying that. All right, so my argument would be is when the filament begins to glow, what it's really doing, okay, is merely taking energy that's already hitting the filament. So let me just draw a cross section of a wire. And so say this was a wire that I was beginning to heat, and it was getting right at the point where it's going to start glowing. And the glow doesn't mean that all of a sudden now there's photons coming out. So before there was photons that we could see, there was photons we couldn't see, right? So you know that the infrared ones were still coming out. And the truth is that we know that there's photons constantly hitting the filament. We know there's radio and microwaves and all the stuff that we're surrounded with all the time is hitting the filament. And my simple argument is that the stuff hitting the filament is lower frequency, right? We're not living in a bunch of gamma rays and X-rays. We know there's a minimal amount. I mean, there's background radiation, there's some, but it's a minimal amount of, ionizing photons. So there's a clear distinction between the, once you go above a certain frequency, like blue light, all right, violet, you're then creating ionizing photons. So all of those photons from violet and above ionize most substances. They cause them to lose electrons. You can bounce electrons off of surfaces with those photons, and the ones below that are a lot less likely to be able to accomplish that task. Now, it doesn't depend on the material, but in most cases, that's the line, is violet. And so what's really happening is that there's also a line between infrared and visible light. And the simple truth is that the infrared light's coming in, say at 1500 nanometers, and the surface is vibrating. The electrons are moving into and out of the surface. That's the heat. The heat is the motion. And the motion is obviously out and in of the surface, right? You could just say there's no, it's not going to be going side to side much. It's going to be going out and in and out and in. That's how the electrons are going to be moving. So they're going to be constantly pushing and flying back. So when one photon hits, when it's moving back, it's going to absorb that energy, okay, because it's moving in the same direction. So it's going to give the electron more energy in that direction, into the surface. So the electron was going back with a velocity of, say, 5, and because the environment has hit it with another piece of energy, it's now going to be moving with 10. Okay, so it's going to oscillate further the other way, and then proportionally swing back on the next turn. It's going to swing back with a higher velocity because you pushed it with a higher velocity. The pendulum's going to swing back. But anyway, the key point is when it is pushing out of the surface, you're going to understand that the electron is going to hit what is coming in, and if what's coming in is occupying this much space, whether you think it's a wave, okay, which I'm saying is nonsense, but let's just say, okay, if you insist it's a wave, you're going to understand when the wave hits the photon's going to compress the wave. So it's going to increase its frequency, all right? And obviously if it's particles, you're going to understand if the particles are spaced, and then I push in, then the spacing of the particles is going to be much smaller. So that's what's really happening. So when the filament's heating, it's not ejecting infrared radiation. It's not ejecting photons. It's not making little bits of force. It's actually just, okay, compressing the force that's in the field. So infrared radiation goes in and it comes back out as visible light because you've increased the frequency. That's what you're seeing. So the energy goes in, it comes back out because the surface is hot. It's pushing out a lot. And remember, when it's going back and you give it more energy going back, that means it's going to come back faster. So the energy's always pushing out, technically. All right. It's never It never really collects the energy unless it's colder somewhere back there. Unless there's a place for it to go, then it can go that way. But the point is that it's under pressure. So just like the Earth, and you push on the Earth here, you're not going to push on the other side of the Earth. You're going to push into pressure, increase the pressure, and the pressure is going to pop out again somewhere else. So if I push something into water, the water rises somewhere else. Okay, so it's going to take the same energy that went in, and it's just going to give it a U-turn. So all the energy being absorbed by electrons is never really absorbed unless all the electrons move. If all the electrons don't move, it's not absorbed, and it swings right back out again, and it gives the next bit of stuff that extra velocity. So that's how visible light is being created, is you're taking infrared radiation going in, or radio waves even, and you're just increasing the frequency. So whatever goes in comes out at a higher frequency. That's what's happening. So you keep increasing the frequency of the stuff reflecting off of the surface. And that's a pretty good explanation for what's happening. And when you get to too high a velocity, that is, if you can actually get the electron to move fast, it can't make a gamma ray because that electron flies out of the surface. So that little piece of energy is not durable. You just lost it, essentially, by moving the entire electron out of the atom, and now you've given it much more motion, and you're not going to be able to recover that in your system. That's your system losing energy. So when you start ionizing the surface, you can't reflect that energy anymore because you're using it to eject electrons. So you're using it up. Yeah. It's a reasonable statement, so I'll pause and see if there's more I'd like to say on this subject. Alright, there really are so many little subjects here. So I'm basically arguing, look, magnets don't produce anything. Nothing flies out of the magnet except what went into the magnet. The magnet's just taking whatever comes in and it's changing the pattern. So unlike the heat example, it's not increasing a frequency, but it's changing what goes out. So I could argue that, okay, electron force goes in, proton force comes out. Proton force goes in, and then electron force comes out. So what comes out at any one location is changed because of the arrangement of the electrons and protons. They change the pattern. So they essentially filter the pattern. So I've made that argument that the distinction could be understood like a bullseye with a blue center and a red ring versus a bullseye with a a red center and a blue ring. And it's the same thing, same amount of red and blue. It's just in a different pattern. And that's what the north and south side are producing. And only other magnets can see that pattern because only other magnets have electrons and protons in an arrangement that can see the pattern. All right, and so then the other thing is like induction. Induction is the same argument. You're changing how the wire or the antenna or whatever is reflecting the energy that's going into it, and it just reflects it different than what it was when it went in. And that's the magnetic part that's being transferred. You're really sending a magnetic signal. And that's why you can only use metal things that you can put electricity into and create a temporary magnetic field. Those are the only things that you can use to transfer this signal. All right, so the idea is also understanding what happens inside a conductor. Probably should make that wider. Okay, so if I have high pressure, the simple argument is, so I have a high voltage, all right, a big voltage, and I put it through a wire. What happens is the speed is quick, and so everything gets hit and it maintains this direction. But the slower the vibration or the movement of the electron is, the more likely these other directions start energy starts moving in the other directions. The other electrons in the atoms start moving, okay, and they start affecting other atoms. So the lower the voltage, the more atoms are going to be affected by the transmission of the energy, and the higher the voltage, the fewer atoms. And that explains why low voltages can create magnetism and high voltages don't work. And also explains why you can transmit much more energy in a very small wire using a high voltage, because you're not spreading the energy in a bunch of directions that aren't the direction you want the energy to move in. So it's just sort of an argument about how much less turbulence you get the faster you go through something, the less other stuff you affect. And the slower you go, the more likely it is the energy is going to get absorbed by friction. So again, it's a friction argument, just like the rolling something on a surface. If I roll two objects and I just do twice the velocity, okay, 1v versus 2v, I end up rolling 4 times the distance, because my friction is going to be less for the object, okay, going faster, because there's less pressure there's less rubbing pressure, if you want to call it that. Gravity is applying less force per inch of surface when it's going fast than it is when it's going slow. So these two things have the same unit of time, okay, and it's the same unit of energy being absorbed by the surface. The same amount of heat is going into this movement that went into this little space. This is exactly the same as this, just proving the point that you're going half your speed here. 3/4 of the way down the track is where you go half your speed, meaning that's where you've lost half your energy. So it's kind of an obvious example that the truth is, the faster something moves, the less it pushes in these other directions as a percentage of its energy. And the slower it's going, the more it loses to the environment in other directions. All right, so that's a good argument. And so we'll do induction and just leave it somewhere around there. So the idea is when you put electricity through a wire, you're hitting atoms in this direction. And the simple argument is the atoms are made of electrons under pressure. So you know that there's electrons on opposite sides, okay, that are distanced between each other because they all are pressurized. They're all feeling each other's presence. They're attracted to the positive nucleus, and the electrons are in their way. And another thing you can understand about that is the argument is why would something, when I push, say I have let me use the color coordination here. All right, so I have a net positive nucleus. Now the point I'll make is it's only net positive. It still has negative components. All right, and so the electron is sitting out here. All right, and the idea is if I push it away for some reason from the proton, the argument would be is there's nothing pulling it back in, right? Because it's getting weaker and weaker. So the force the force of the positive is getting less and less strong. But the thing to remember is, so is the resistance of the electrons. So if I draw this bigger, you have an electron over here, an electron over here, and you say you have your positive there. You can sort of understand that as this object moves in this direction, that it's getting further away from the proton. But the fact is, these angles mean it's getting away from the electrons even faster, in the sense that the R² rule is basically saying that this force of repulsion is getting weaker, okay, at the same time this attractive force is getting weaker, except this is getting weaker faster, okay, so at a faster rate, because it's two objects and they're both not at a straight line. They're at a longer distance than that straight line. And so that's the compensating force. So as the object gets further away from the proton, the force that's going to attract it back is the fact that the net force is going to be less out here, in the sense that the protons will be more attractive out here because the electrons are less visible. So the further away you are, the brighter the proton and the less bright the electrons. And the closer you get, because the electrons are closer, they get very strong, and so the attractive force to the proton isn't enough to push you through that electron barrier. And this also explains why when you want to combine atoms, you have to break that resistance. So for some chemistry, you have to break the resistance of the electrons to be able to force another electron into the atom. And that's the whole idea, is you have to break through that barrier being created by the electron pressure. So you have to add energy to put the object inside the nucleus, or inside the orbitals that aren't orbiting. They're just positions in space. And you have to push through to get another electron inside one of those inner orbits. All right, so that's yeah, I wasn't going there, but it's an important it's a good thing to understand why, when you push an electron out of a surface, why it comes back in. It not only comes back in because there's force hitting it from the outside universe, but it also, that's integral to the fact that the force is going to be deciding how much electron and proton force there is also. And that's changing as it moves positions. The forces affecting it are changing. And in the case of that electron, the proton is getting stronger as the electrons get weaker. The net influence is towards the proton. Okay, so induction, back to the conductor, is just the radiation again is coming from the external universe hitting the wire. And all that you're doing by pushing electrons this way, you can understand that the electrons, when you hit an electron in this way, you're basically squeezing the atom. So you're squeezing the atoms this way, and by doing that, you're pushing these electrons out this way. And critical to that event happening is the fact that you're hitting a lot of atoms and you're not hitting them too fast. So the lower voltage works, the higher voltage doesn't. In the case of getting the most out of this event of pushing electrons and creating the induction. All right, so all you're really doing then is pushing electrons on the surface, and again creating a pattern, because you have a higher pressure here and a lower pressure, higher pressure higher pressure at what end? Well, it doesn't really matter. The point is that this just creates the field, because you're polarizing the atoms by pushing the electrons in one direction. And the fact is, you have to keep letting the electrons collapse again before you can push them again. So that's why you need alternating current. You need alternating current because the electrons have to go back. So the atoms have to expand back this way again, pull the electrons back in. So the atoms have to keep doing something like this for you to be able to create an oscillation on the surface, a vibration on the surface. If you use DC current, then you just push these out and they never fall back, because you just keep continually pushing, you keep squeezing the atom, and you never let the atom go back to its natural shape. So you just keep putting pressure on it and keep squeezing the atoms, and so they never bring their electrons back in. So you need the electrons to oscillate in and out of the surface to be able to change this, what reflects. How it reflects can only be changed by the fact that the surface is vibrating. If the surface isn't vibrating, then it just reflects as it came in. And you have to change that pattern to create a signal to the rest of the world that you changed the pattern. Alright, so I could go a step further and talk about how photons are received on a surface, but that gets into other videos where I've already explained how photons function as bits at a frequency and all of that, and that's a little more complicated than I want to get to. So I'll pause and see if I need to clean anything up. I guess I should say something about the direction thing. So the idea is if the electricity is going this way, the argument is that yes, it would be nice if it was perfectly perpendicular, but the idea is it sends the signal not perfectly perpendicular. And so the idea is that the pushing is in a direction, which means it'll add momentum in that direction. So the signal could come in this way and it's going to leave this way. So the pattern is now directional. And so if the electricity is going this way, then the pattern is going to be pointed that way. When the signal's the other way, it's going to be pointed the other way. And so that creates the capacity for the effect to be seen as positive and negative, or north and south. Okay. Because the vibration is essentially going in and out of the surface in the direction of the motion of the force in the wire. Yeah. I like that good enough. I'm just thinking that you could think of that both ways, as I pointed out before. So the energy is going out this way, and where it's relaxing in the other part, it's pushing in this way. Okay, the electrons are coming in this way. So at one side you're pushing force out, and the other side you're when you're relaxing, you're pushing it in. You can see that obvious difference. So when the energy is going in, it's going in this way. When it's going out a little bit that way, because of the change in the momentum between the perpendicular force you're hitting and the way the original voltage was moving. You have to combine those momentums in the end. Alright, so one thing I thought of, I didn't want to say something too that yes, I'm trying to do this, concisely. So you can have radio antennas, all right, and you can put high voltages into them and cause this effect. And because what you've basically done is taken a huge amount of mass, and so now you're going to try to put a lot of energy into this giant structure. And so you can get more wattage into the structure if you use a higher voltage, and it will spread because you're putting it into a gigantic structure. So the bigger your antenna is, the thicker it is, the more dense it is, the more massive it is, the more capable it is of getting the energy to the surface, and that's the important part. But when you're using high voltages in a wire, the trick is that you're using less of the wire to move the pressure. So the higher the voltage, the fewer atoms you're involving. But if you increase the wattage, then you're guaranteed that everybody's going to be moving anyway. And again, like I said, depending on how big your antenna is and how far you want to broadcast, you can pump more watts in as voltage, because it's going to dissipate that pressure into a lot of atoms anyway. So even though it's moving at a high speed, by the time it gets through all the density of the antenna, it's not going to be going so high. The voltage isn't going to be that high. So that's why that works. You're putting a high voltage over a huge surface, and doing that reduces the net voltage. All right. Yeah, that's good enough. All right. So let's see what other comments there are. Yeah, that is not the right comment page. There we go. I don't know if let me just read Superior Mind here. I didn't really get his point, but anyway, I had an odd thought. Near the center of a massive planet, the force that provides the push of electrons and protons together could be received at an even slower rate near the center of the planet. So the center just is the fact that it's the smallest density of material with the most stuff going through it. So I think that's the safer way to understand it, is that whatever energy is coming from the exterior, okay, of a circle, so you can understand that the energy is going to hit all of these locations. And the fact is, in the center, all of that energy, okay, has to go through the smaller and smaller amount of mass. So the reason why it's hotter in the center is because that's the place the most energy is going through, and it's the least mass. So obviously it gets hotter. So it's the same heat in total. The amount of heat going through this whole crust here is the same heat that's going through this little bit of crust here. Okay, so that's why the center is much hotter. It's just because there's a lower density of matter, and the same vectors of force are going through the smaller density of matter. So if you just took any object and just, oh, you can't see that, right? Yeah. Oh, Jesus. This is a complicated thing, having to do this all on my own. All right, so the point I was making was you could just take any layer and just recognize that it's a huge amount of mass here, that the same energy that's going here is going to be hitting this mass here. So anywhere you draw this line, you can recognize that the same amount of energy that's going to hit this outside has to hit this here, and it's a much smaller amount of mass, so obviously it gets much hotter. So the center of the Earth is some, 4,000 degrees, something like that, Celsius. And it just gets colder and colder as you go further out, because there's a huge amount of matter. So the center isn't doing anything special. It's just that it's much less matter having the same amount of force go through it. Okay, it's more concentrated. It's a greater density of force to matter bit, you could argue. And there's a low density of force to matter out here on the outside. So this gets back to the whole gravity argument, and it's just about what's above you coming in, and then what's below you coming up at you. And the point is, it doesn't matter the vectors, because all the vectors side to side are always equalized, because there's no other body messing anything up, and it's just the vectors coming up, that have a component in the up direction that are going to be affected by the Earth being below me and such. I don't know if there's any need to go further. I mean, the science and math guy, I'm not going to do the third part on gravity just because it was so boring, but he talked a little bit about drilling a hole through the Earth and how you have no gravity in the center. But it's not really the truth, because what he did say was, well, you can't do that because the center of the Earth is molten. And it's not just molten. It's under extreme pressure, because there's pressure going in all directions towards that center. So the center is under extreme pressure. So even though there's less gravitational force affecting you, the force of the rest of the matter being under very high pressure means there's no way you could create a vessel that could withstand the pressure. Nothing you could build could go into the center of the Earth and protect you from the pressure. And so the pressure is just the gravity getting to you in another way. So the gravity's still there in a sense. The force is still there. It's just in the form of matter moving instead of in the form of force moving. But the matter can't move without the force pushing it. So you can understand it's the same amount of gravitational force is hitting you. It's just that it's doing it literally in both directions now. All right. That should be understandable. Well, by this audience, who knows? Okay. All right, so, oops, I don't need that. So it says, all right, right near the planet. So I'd expect that the balancing effect which holds matter together, pushing electrons and protons together, could be off. So it's not off. It's, it's just the same, it's just the same pressure. And the fact is that you've concentrated the delay part, okay, in the sense that it's not getting through the matter as fast, but in the center, it's not getting to the center as fast from both sides. But the matter itself is now moving, okay, which will cause it to come apart, unstable atoms, and depend on some external bias like pressure, blah, blah, blah. There would be probably some swirling effect. So the swirling, any swirling effect is probably just because the Earth is in fact spinning. So obviously if you put water in a bucket and you spin the bucket, the water in the bucket spins. So there's probably plenty of turbulence, to some extent, in the sense that the molten Earth is given momentum by contact with the spinning parts. All right. So this guy says the energy formula is direct consequence of Newton's second law. So this guy's at least conceding that that's their perversion. So in spite of the fact that Newton said nothing about squaring a velocity, didn't say anything about any quadratic increase in energy, didn't make any reference to it being true at all. Okay, they just keep saying he said it and he didn't say that. Okay, if you think the formula is wrong, then you must also think the most basic theory in physics is also, yes, it's exactly my point. So I'm sorry you didn't realize that. Yes, that's exactly my point. I'm saying you have broken your physics entirely. You have a bunch of wrong answers to a lot of equations and questions because you've used this nonsense. You didn't even measure an electron correctly in terms of its mass because you used mv squared to measure it. And so you way overestimated the importance of the velocity as being part of its momentum and thought its mass must be really, really small because you thought its mv squared was its velocity. So if you used momentum to decide how much mass the electron had, obviously you wouldn't have skewed the energy as being higher percentage velocity, and therefore the mass would have to be a much bigger number. And so you would have calculated the mass of electron much higher, much heavier. So yes, it's ruined your physics. That's my whole point. Okay, and it's nonsense. It's 9.8 meters per 1 second per 1 second. There's no second squared. It's just an added acceleration every second, if you want to say that. And the point is, it's just an added acceleration. So you could just say 9.8 meters per 1 second. And that's exactly all it is. It's 9.8 meters per 1 second. 9.8 meters of distance is what you're going to get every second. 1 second, not any number of seconds. All right, so Superior Mind says, what? Acceleration results from linear change of force applied relative to mass per unit time. So again, I don't see why you just don't say acceleration is just an increase in velocity. And you can increase the velocity once, or you can do it twice, or 5 times, or 50 times. You can do it 10 miles an hour the first time, and 5 the second, and 3 the third. Or you can, in the rare case of a constant force, and I'm saying it's a rare case, there aren't very many of these things called constant forces. Gravity is the only one I know of. Yes, it's every second the same amount of force pushes on something and gives it an increase in its velocity. And that's all. And I'm just saying the formula proves it. You know it's only 2 seconds in gravity is only 19.6. It isn't anything higher than that, and yet you're saying it's 4 times the energy. Twice the time, 4 times the energy. No reason to believe that. How does this translate to squaring velocity when determining how much impact this thing will have? Its momentum, total force equals total stored motion energy. It's not the way I would have said it, but okay. Will always be scaled by mass via total mass and velocity. The point is momentum always works, and so show me a circumstance where momentum fails to get a right answer. So that's all. Just show me where I'll ever go wrong using momentum and ignoring kinetic energy entirely. Show me the circumstance where it crashes on the moon. Okay. So my argument to you is that they landed on the moon calculating momentum of thrust. They didn't use kinetic energy, because if they used kinetic energy, they would have the thrusters on a different amount of time, and that didn't happen. Or they would have to concede that, well, the energy out isn't going to be equal and opposite. The thrust energy is not going to equal how fast the spaceship moves, so it's not going to obey Newton's third law. So you either say Newton's third law is garbage, okay, or you concede that no, it's momentum that landed on the moon. The 0.05 squared is some kind of shit. It's a made-up concept with no accurate actual application. The point is there's no evidence of it ever being conserved when you transfer it from objects of unsimilar mass. So anytime you convert energy from one mass to some different mass, you will either have to make free kinetic energy or you will have to lose kinetic energy. So the mass is the scalar multiplier in both cases because it's just a linear relationship of mass and force. The linear relationship is mass and velocity, but whatever. I mean, velocity and force. In most cases, you're not changing the mass, but whatever. Although technically force is just single units of momentum, right, but there's single units of momentum in the sense that it's equal little bits of force, so it's quantizable, and it's really just about its velocity. And you're just going to transfer the velocity of the little masses into the bigger mass, which stack based on how many forces of the mass is made of. Now, so you're just collecting force. When you collect little force bits and they stick to you, you share your momentum with them. And that's the simple thing that's happening. Electrons and protons are collecting force bits in a direction, and as they do that, they carry the force. They're force carriers. All right, matter is made of force. So matter isn't made of force. So that's, I don't know where you went with that, their superior mind. However you want to say it, matter is made of force. No, it isn't. Matter is dead as dead could be. It doesn't have any ability to move until a force sticks to it. So until it consumes a force, occupies it, absorbs it, however you want to describe it, it doesn't move. And so it's collecting force, and it can give the force to other electrons, and that's how it exchanges the force. All right, it's all forces in various directions one way or the other, so I don't agree with that. All right, I don't know if all this is worth reading, but I'll read it. You have F equals ma, and F and A are vectors. So this is all your jabber. So he's going to try to do some scalar crap here or something. All motion is vectors. It's just idiotic to say there's any other kind of motion but a vector. All motion has to be in a direction. There's no such thing as motion in no direction. Now, if you know the basic linear algebra calculus, you can multiply both sides with an infinitesimal vector of displacement. Again, irrelevant. That's not going to square anything. dr via the dot product. You're just saying that because the acceleration happens in 1 second units, that somehow you're going to change that and say it's the number of seconds, say 5, and I'm going to square the 5. It's only 5 seconds. It's not 25 seconds. So you're making up a stupid excuse to somehow square the number of seconds it's in a force, and there's no reason to square the number of seconds it was in the force. It was only in the force 5 seconds. It wasn't in the force 25 seconds. So you get drfma blah blah blah, where used acceleration derivative of velocity. Let's see what. Oh, look at all this crap. No, I don't think we're going to bother with all that. It's just more of this crap. Okay, so no evidence, no experiments, just crap. Crapomatics. Okay, there's no mv squared. There's no squaring v times v. These are all mistakes you're making. Where you're presuming that because you called it an acceleration, that somehow, no matter how many seconds you accelerate, it's that many seconds squared. And it's simply not. All right, so we'll read the end. Let's see, aka velocity. Okay, this is not magic. It's bullshit is what it is. It's mathocrapics. Crapomatics. The momentum is also a state function. It's also a state function. That's what it says. And it also is linked with the force by Newton's second law. So he's doing it again. So we know Newton just said the simple thing. Force equals the change in your momentum. And if you want it as a rate, you put it over time. So that'll give you 9.8 meters per 1 second if you want to. But if you ignore time and just say, what's the net force? You just cross the T out. Fuck it. The net force is 1 unit. You just get rid of that, and clearly it's F equals the change in your momentum. The force is momentum. That's what gravity actually creates. Okay, your momentum right now, standing still on the earth, is in fact, you can measure it with a scale. It's 1 mile per hour. So you're moving 1 mile per hour. I can't remember how many meters that's per second that is. 0.4, something like that. You're moving that into the earth right now. That's what the scale is showing you. Because you could move you horizontally into a scale. And the amount of velocity I give an elephant, if I give it 1 mile an hour, it'll weigh elephant. If I give a mouse 1 mile an hour, it'll weigh mouse on the spring, on the scale, demonstrating that all gravity's doing is giving you momentum. It's not giving you anything else. All right. Newton's second law, F equals blah, blah. You can do the exact same derivative for connection between torque and angular momentum. So angular momentum isn't anything special. It's still just little pieces of mass in different locations moving a velocity. It's still just momentum. All right, by taking the cross product of dr instead of the dot product, so that doesn't mean anything. All right, so just mushomatics. So he keeps talking. And also, your comment contains so much mistakes. For example, acceleration results from linear change of force. So, yeah, I don't see the point in that, and it's just force and time. You know, how much pressure for how long. And obviously, like an impulse, I could drop something on a scale, and it can only apply a pressure, and it's all gone. It uses it to compress the spring, and then the spring can shoot it back. It's all over because it can't apply a constant pressure. And so it's just about the time. A constant force means that the time is in second units or whatever the units are. We don't need to change the force to experience acceleration. So that's obviously just idiotic. You don't need to change the force to experience acceleration. Absolute nonsense. The same force will not cause you anything unless you're resisting something. So you can't say that. The same force, you can't accelerate or decelerate unless you change the medium you're moving through or something. But there's no way you can change the acceleration without changing the force. If you were correct, then the laws would have been FD dt. Yeah, that's the truth. It's about the time. And it's not. But it's not. It says you. If you want to change something to be equal to acceleration, you need to use the potential energy. So again, this is just, again, I've been over this so many times. Potential energy is such a misused term. The objects you're talking about have no potential energy. Okay, they're just in circumstances where you're going to put them in a field of energy. and they're going to acquire energy. But a boat sitting on the side of the Mississippi River doesn't have any potential energy. All right. And you have whatever, blah, 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 blah. Okay. Don't take this guy DraftScience seriously. So again, don't take seriously people who refuse to provide any experimental evidence to defend their arguments. So they're going to claim something's true. They're going to claim it's true for 300 years. They're going to claim all their science knows it to be true, and yet they can't produce a single fucking physical experiment showing it to be true. All right, watch him purely for entertainment, but all seriousness, he doesn't know anything he is talking about. Well, you're going to be proven wrong, and what should be your penalty? So you just let me know. All right, I won't block you, I'll just delete you. But let me know. What should your penalty be if you're entirely wrong and you're just talking shit at me? What do you think would be an appropriate penalty for you to pay for the offense you've committed against me? Just curious. Shit talkers like you, what do they deserve? You tell me. All right. So this stupid mop head again. Where did you learn that Leibniz wanted to prevent Newton from publishing? I couldn't find any info about that. So there was the letters between Clarke and Leibniz. And the funny part was, is Leibniz sends them to the Princess of Wales. So she's very highly connected, obviously. Okay, like has the king's ear. Pooping about how Newton is ruining religion. And obviously the king knows that religion is really important to him staying king. Okay, so this is indicating that Newton is some sort of threat to the whole structure of their civilization. And that's shit talking, frankly. Okay, and Leibniz did it all the time. He was constantly ragging on Descartes and Newton. Just a fact. And this went all the way to the 1700s. So after Newton was dead, about 20 years after Newton's death, they were still shit talking with this Leibnizian nonsense. All right, still saying, oh, Newton's wrong. And so it was a whole controversy, fuckhead. And so, people had labels of Newtonian. Okay, that's what they called them, the Newtonians. Okay, because they had to defend themselves against this new modern living force physics. And again, no physical experimental evidence, just rubbish. I mean, it's just a terrible history in science. It just is. I mean, everything was disorganized. Rich people published. There was no science organization of any kind of real stature. Even the, whatever they call it in England, hadn't fully functioned and wasn't really paying its bills. And so there wasn't any place where science was really organized. And so a lot of it was a competition between different countries, and they all wanted to say we invented it. And so it's all kinds of crap in there. And it's just an absolute fact. And so this guy goes through all this nonsense trying to say, oh, no, that's not what was happening, blah, 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 blah. And just a waste of time. All right, so I said in the last comment to him, clearly the letters have been edited. All the introductions and salutations are missing. So I did link him to a set of the stuff because he says he can't find it, right? So there's a whole bunch of different versions and all that kind of stuff. And there's millions, literally, of Leibniz letters, okay? Leibniz talked to everybody, wrote to everybody. So there's a ton of information you can read of Leibniz's. But unfortunately, 90% of it is religious gibberish about solitons and monads. And it's impossible to understand what the fuck he's talking about. And he's basically incoherent most of the time. So if I write the mayor of your town talking about what a stinky person you are, you wouldn't consider that a threat. The very fact that he begins his letter with a claim that religion is on the decline, implying Newton is the problem. Do you have to explain to you how kings use religion through control the masses? Use religion to, I guess that should have been through. Well, anyway, His response is, so his last one, I didn't bother reading it, frankly. It's just, this is just proving that these people don't give a shit about the facts here at all. They're going to keep trying to argue that Newton believed in mv squared, when clearly for 100 years this was argued as an argument between very diverse answers to the same question. You ask a simple question, how much energy does it have? The two factions have a different answer for the same question. You can't get clearer as a controversy, for fuck's sake. And to say it's semantics, to say that it doesn't matter, whether it's 10 or 20, or in the case of a bullet, 1001. These are gigantic differences in the answer. All right. That's not the same as asking a king to censor somebody. So whatever. See, this is just, he didn't answer the question. So it really would be okay with you if I went to the cops and implied you're kind of a troublemaker and they ought to be on the lookout. That wouldn't bother you any. All right. Leibniz and Newton had their disputes about calculus. So this is just the bullshit. No, it was a dispute about absolute space, relativity, mv squared. Okay, it was clearly one of the arguments. The lever was brought up by Clark. I mean, fuck you, you're wrong. Okay, there was some bad blood between them, and Newton had unjustly, so this is the big lie. So Newton had unjustly claimed that Leibniz has plagiarized him. That's not how it happened. Leibniz made the accusation to Newton. Now, other people had made the accusation to Leibniz, okay, merely because they knew Newton did it first. And then Leibniz decided to double down and say, okay, well, if you're going to say I stole it, I'm going to say Newton stole it. So Newton didn't say a damn thing. He didn't give a fuck. He didn't want the credit. He didn't care who invented it. He didn't care about any of it. But as soon as Leibniz accused Newton of stealing, that's when Newton got pissed the fuck off. All right, and the fact is that Leibniz forged documents, the dates on documents, to try to show that he did it 10 years earlier, when everybody knew Newton, by more than one witness. He had sent letters about his calculus to more than one person, so it wasn't just one person's letters that proved Newton had it 10 years before he published it. 10 fucking years. All right, and so this is how they're just remaking history up. They're just making up this fake crap because Newton was the head of the imperial organization or something, and because of that, because Newton picked who was on the jury, somehow Newton was guilty, when that's bullshit. The only person that traveled anywhere and talked to everybody is Leibniz. Leibniz was in England. Leibniz read Newton's earlier letters that were public, by the way. Newton didn't read anything of Leibniz's. Newton didn't go to Leibniz's library and see a bunch of Leibniz's private letters. Newton's letters were the ones that were public. Okay. Would you say that Newton tried to censor Leibniz first? So what a liar. So I almost feel like blocking you, but this is such a perversion of the truth. It's just such a fucking lie. God, you just can't do better than that, huh? You can't do better than just lying about Isaac Newton? Ugh, disgusting. Yeah, I'll let you, we'll see. But fuck you. There's no controversy. Yeah, there was and there still is. It's just you're too ignorant to accept any of the facts. You'll never show me a piece of fucking evidence, you fucking weasel. Show me a fucking piece of evidence. Show me your KE conserved somewhere. Show me the thermometer in the ballistic pendulum showing me that there's 1999 joules of heat in there. Show me some piece of evidence, you fucking weasel. Ugh, it's just disgusting. All right. So the other liar, this guy with the no neutron. So does the atomic bomb work? I had to point out, I didn't say there was no neutrons. I just made the simple argument that I can show a ton of other physicists talking about now. of, the fact that neutrons decay into an electron and a proton. Everybody knows it. So why is it a fucking argument? Why is there any argument? It's the simple answer. Yes, there are electrons in the nucleus in the form of half of the neutron is an electron. Fuck, I just can't believe you people are just so fucking dishonest. So fuck that stupid comment. Alright. Let's see. Veritasium's videos are way better than yours. Yeah, that was a really brilliant comment. Oh, fuck. Yeah, he has people and $1 million. Oh, his videos are better than mine. What a surprise. Let's see. You think you can calculate what happens in a collision based on momentum alone? Yes, of course. Show us. Give us an example. Give me the example and I'll show you. I mean, it's very simple. MV in, MV always out. So what's the complication? I already did bowling ball. So there's bowling ball examples. And so you just look up bowling ball, search my channel. And I did the whole dissection of the ball hits the pin, the momentum is exchanged, the momentum is exchanged, the momentum is exchanged. That's all it can exchange is momentum. The ball loses momentum, the pin gains exactly the same amount of momentum that the ball loses. So what example do you want, you fucktard? You're the one who has provided no evidence. You've had 350 years to show me something and you still can't show me nothing. You haven't done any experiments, you fucking little weasel. God damn. Well, the video that I was commenting on wasn't about physics. I was trying to say that you lied about physics even though you do. Or whatever that is. What I was saying is that deleting comments is just a way for people like you to attempt... Yeah, so it's just bullshit. Sorry. No, deleting is necessary because all it is a bunch of lies and false premises that you jackasses put on the internet. And I have no obligation, again, to waste my time with liars. So if you can't premise your argument with something other than preposterously stupid lies... Yeah, I don't have any obligation to play with you. I just don't have the time or the interest to sit there and undo your lies. Waste of my time. And I value my time. Alright, so we already did the bet for $5,000. The undisclosed bet. The terms of the bet are completely undiscoverable. Alright, so that's enough, I think. Had my fill anyway. Ugh, assholes. That's all there are. Alright, so, till the next time and such, and so forth and whatnot. It really has to be an argument about evidence. I mean, I've gone through, like, Stern-Gerlach. I showed the muon experiment. I mean, we have to argue experiments somewhere. So you have to show me your great experiment demonstrating some of this crap. And you don't have any great experiments, and that's the absolute truth. And let's just remember, physicist Michael was supposed to produce one of these great experiments, and he completely weaseled out. He completely fucked the lever one by putting clay on the lever, to protect his car. No, that won't fuck up the experiment any. Oh, that was just so fucking stupid. No, it's just so pathetic. Alright, so anyway, till the next time and such, and so forth and whatnot. That's it. Had my fill.